Entropy is one of physics' most essential yet widely misunderstood concepts. Often described vaguely as disorder or chaos, entropy is far more profound. It's about energy, information, and the irreversible flow of time. It governs everything from cosmic evolution to everyday events. Let's start with a simple image, a sandcastle on a beach. Carefully sculpted, each grain is part of an ordered structure. But when the tide comes in, the castle collapses and the grains scatter randomly along the shore. That transition, from a specific arrangement to countless disordered ones, is a glimpse into what entropy really means. Entropy isn't just about messiness. It's about how many different ways a system's components can be arranged. The more possible arrangements, the higher the entropy. In the 19th century, physicist Ludwig Boltzmann formalized this idea, showing that entropy measures the number of microscopic configurations consistent with a system's macroscopic state. For example, a box of gas can look the same pressure and temperature, even as its molecules constantly move in countless different patterns. Similarly, a shuffled deck of cards has more possible configurations than a neatly ordered one, meaning higher entropy. This idea is central to the second law of thermodynamics, one of the foundational principles of science. It states that in an isolated system, entropy will stay the same or increase over time. It never decreases. That's why hot coffee cools instead of reheating itself. Heat spreads into the air, increasing the system's overall entropy. Nature favors states that are more statistically likely, those with more ways to exist. But entropy isn't just about increasing disorder. It drives the processes that shape our universe. Take the sun, for example. Nuclear fusion turns hydrogen into helium, releasing massive amounts of energy. This energy radiates outward, increasing entropy, but also enabling life by fueling processes like photosynthesis. One common misunderstanding is to equate entropy purely with chaos. A broken glass may look more chaotic than a whole one, but it has higher entropy not because it's messy, but because there are vastly more ways for shards to scatter than for them to stay intact. Entropy is about probability and energy distribution, not just visible disorder. Entropy also gives us the arrow of time. Most physical laws work equally well forward or backward in time, but we know a video of a glass shattering is playing forward, not in reverse. That's because entropy increases only in one direction. This rise in entropy gives time its forward flow. Even daily tasks reflect this principle. Making your bed or doing the dishes reduces entropy locally, but uses energy that disperses as heat, raising entropy overall. Likewise, engines can never be perfectly efficient because some energy always escapes as unusable heat. This limitation, imposed by entropy, is why perpetual motion machines are impossible. Living things seem to resist entropy by creating order, complex cells, organs, and systems, but they do so by constantly exchanging energy and matter with their surroundings. Humans eat food, maintain bodily structure, and release waste and heat, ultimately increasing entropy beyond themselves. Life doesn't break the second law, it operates within it. Even our creativity reflects entropy. When solving problems, the mind explores countless possibilities, configurations of thought, before settling on a solution. Just as entropy guides systems toward more probable states, thought unfolds in a sea of mental options. Entropy also links deeply to information theory. Claude Shannon showed that randomness and information are mathematically connected. A book in an unknown language may look like gibberish, high entropy, but to someone who understands it, it contains rich information. Data compression, for instance, reduces redundancy and thus lowers entropy. And in the 1960s, physicist Rolf Landauer showed that erasing information actually increases entropy, releasing tiny amounts of heat, proving that even computation obeys thermodynamic laws. The universe itself began with remarkably low entropy at the moment of the Big Bang. Since then, entropy has steadily increased, giving rise to stars, galaxies, and life. That low entropy beginning is what allows time to move forward. But why the universe started that way remains a deep mystery, with explanations ranging from statistical anomalies to multiverse theories. On a cosmic scale, black holes represent extreme entropy. Physicists Jacob Bekenstein and Stephen Hawking discovered that a black hole's entropy is proportional to the area of its event horizon, not its volume, implying a vast amount of information. Black holes slowly emit radiation, Hawking radiation, lose mass, and increase entropy in the universe until they eventually vanish. This leads to profound insights about reality, like the holographic principle, which suggests that all the information in our universe might be encoded on a two-dimensional surface, much like a cosmic hologram. If the second law continues to hold, the universe will ultimately reach maximum entropy, a state known as heat death. At that point, all energy will be evenly distributed, no work will be possible, and stars, galaxies, even black holes will be gone, leaving behind a cold, dark void. While sobering, this future also emphasizes how rare and beautiful our present moment is, a universe bursting with structure, complexity, and life. In the end, entropy is more than a physical concept. It's a lens for understanding time, life, creativity, and even the limits of knowledge. It reminds us that change is constant, order is fleeting, and in a world tending toward randomness, the moments of clarity and meaning we create are all the more remarkable. Special relativity. Imagine you're on a train, moving swiftly along the tracks. Inside, everything feels normal, calm, steady, as though you're not moving at all. But to someone standing outside, you're racing past at high speed. This contrast in perspective lies at the heart of Einstein's special relativity. At its core, special relativity tells us that the laws of physics are the same for all observers moving at constant speeds, no matter how fast they're going. This principle leads to a groundbreaking insight. Space and time are not absolute. Instead, they're woven together into a single entity called space-time, which can stretch and warp depending on how fast an object moves. One of the most surprising aspects of special relativity is the constancy of the speed of light. No matter how fast you're moving, toward or away from a light source, you will always measure light speed as 186,000 miles per second. This fixed speed leads to profound consequences, like time dilation and length contraction. Time dilation. As you move faster, time slows down for you relative to someone at rest. For example, an astronaut traveling near the speed of light might age just a few years, while decades pass on Earth. This isn't just theory. Experiments with atomic clocks on airplanes and satellites have confirmed it. Length contraction. Similarly, objects shrink in the direction of motion when observed from the outside. A spaceship traveling close to light speed would appear shorter to an outside observer, though nothing changes from the perspective of those on board. This contraction is real, not an illusion. It's a result of space itself being compressed in motion. These effects, time slowing and space shrinking, might seem bizarre, but they stem directly from the idea that space and time are relative, not fixed. This represents a major shift from Newton's view, where space and time were considered unchanging and universal. Experimental proofs. Evidence for these ideas isn't limited to thought experiments. High-speed particles known as muons, created in Earth's upper atmosphere, live longer than expected because they're moving fast. Their internal clocks run slower due to time dilation, allowing them to reach the ground before decaying. The speed of light as a limit. Perhaps the most famous implication of special relativity is that nothing can travel faster than light. As an object nears light speed, it takes more and more energy to keep accelerating. To actually reach light speed would require infinite energy, which is impossible. This sets an unbreakable speed limit in the universe and restricts how fast we can send signals or travel across space. Why it matters. Although special relativity's effects are most noticeable at extreme speeds, the theory has very real implications for our everyday technology. GPS systems, for instance, must account for both time dilation and general relativistic effects to provide accurate positioning. Despite its counterintuitive nature, special relativity has passed every experimental test. It forms the bedrock of much of modern physics and continues to shape our understanding of the universe. It forces us to accept that time, space, and motion aren't as fixed as they seem, and that our everyday experience is just one small part of a much stranger reality. Black hole physics. Imagine a point in space where the familiar laws of physics no longer hold. where the very forces that govern the universe collapse into something unknown. At the heart of every black hole lies such a point, the singularity, a region where gravity is so overwhelming that space-time itself bends and breaks. This is where black hole physics begins, a field that pushes the limits of our understanding of the cosmos. Though the idea of a black hole dates back to the 18th century, it was Albert Einstein's general theory of relativity in the early 20th century that provided a framework to understand their formation and behavior. According to this theory, when a massive star collapses under its own gravity, it can create a black hole, a region in space where gravity is so intense that not even light can escape. Once you cross the event horizon, the boundary of a black hole, there's no coming back. Black holes aren't just strange, they're fundamental to probing the deepest laws of nature. They challenge and inform our understanding of gravity, quantum mechanics, and thermodynamics. A key to grasping their behavior is the concept of escape velocity, the speed needed to break free from a gravitational pull. For most celestial bodies, this speed is manageable, but in the case of a black hole, the escape velocity equals or exceeds the speed of light, rendering them invisible to our eyes. We only detect black holes indirectly, through their effects on nearby matter. One of the most intriguing aspects of black holes is how they affect time. As you approach the event horizon, the intense gravity causes time dilation, making time appear to slow down from an outside perspective. For the person falling in, however, time moves normally. From the outside, you'd appear to freeze at the event horizon. At the very center lies the singularity, a point of infinite density and curvature where our current physics breaks down. What happens here remains one of the greatest unsolved mysteries in science. Even though we can't see inside a black hole, we can study what happens around them. Matter drawn in forms a swirling accretion disk, which heats up and emits X-rays and other radiation before crossing the event horizon. These emissions allow astronomers to locate and study black holes from afar. Contrary to the popular image of black holes simply devouring matter, they also play active roles in shaping the cosmos. As material falls in, the energy released can influence entire galaxies. For instance, the supermassive black hole at the center of our Milky Way may drive some of the most energetic phenomena in the universe, such as quasars, exceptionally luminous and distant sources of radiation. Black holes are also at the heart of one of physics' biggest puzzles, uniting general relativity, which governs large-scale structures, with quantum mechanics, which rules the microscopic world. These two pillars of modern physics don't yet agree under the extreme conditions found at a singularity. Unlocking the secrets of black holes could pave the way for a unified theory of quantum gravity, a holy grail in modern science. One of the most profound breakthroughs in black hole physics came in 1974, when Stephen Hawking proposed that black holes aren't completely dark. Through quantum effects near the event horizon, they can emit what is now called Hawking radiation. According to this theory, empty space is actually buzzing with virtual particles that pop in and out of existence. Near a black hole's event horizon, these particles can become separated, one falling in, the other escaping as radiation. Over immense timescales, this causes the black hole to slowly lose mass and evaporate. This revelation introduced another mystery, the black hole information paradox. If black holes can evaporate completely, what happens to all the information they swallowed? Does it vanish forever? This question has profound implications for our understanding of information, entropy, and the laws that govern the universe. Despite major advances, many questions remain. We still don't know exactly what occurs at the singularity or how to fully reconcile the contradictory predictions of relativity and quantum mechanics. What we do know is that black holes are among the universe's most fascinating and mysterious entities. They stretch our understanding of space, time, matter, and information, and they will continue to be key to unlocking the deeper truths of the cosmos for generations to come. Gravitational waves. Imagine standing beside a still, quiet pond. The surface is glassy and calm, mirroring the sky above. Now, toss a pebble into the pond. Ripples radiate outward, disrupting the smoothness. Now replace the pond with the fabric of space-time itself, and the pebble with an event of unimaginable scale, like the collision of two black holes or a massive stellar explosion. The ripples created in this cosmic pond are known as gravitational waves. Gravitational waves are one of the most astonishing and profound predictions of Albert Einstein's theory of general relativity. They represent literal ripples in space-time, waves produced when massive objects accelerate, causing subtle distortions in the very structure of the universe. These waves travel at the speed of light, carrying information about some of the most energetic and violent processes in the cosmos. Theoretical foundations. According to Einstein's theory, space and time are not separate. Instead, they form a single, four-dimensional continuum known as space-time. Massive objects like stars, black holes, and planets bend and curve this space-time, much like a heavy ball resting on a stretched rubber sheet causes it to dip. This bending is what we perceive as gravity. Now, if these massive objects move, particularly if they orbit one another, they can send ripples through space-time. These are gravitational waves. Much like ripples on water, they stretch and compress space as they travel. However, the changes they cause are incredibly tiny, far beyond what humans can feel or detect without specialized instruments. From theory to detection. Einstein first proposed the existence of gravitational waves in 1915, but even he doubted they could ever be measured due to their faintness. For decades, the idea remained purely theoretical. That changed dramatically in 2015, when scientists using the Laser Interferometer Gravitational Wave Observatory, LIGO, made a historic discovery. They detected gravitational waves for the very first time. These waves came from a collision between two black holes, roughly 1.3 billion light-years away. LIGO picked up this cosmic event using laser interferometry, an extremely precise method where laser beams travel down long tunnels at right angles to each other. When a gravitational wave passes through, it slightly alters the distance the beams travel, causing an interference pattern that can be measured. The shift is minuscule, on the order of 1,000th the diameter of a proton, but LIGO's instruments are sensitive enough to detect it. The detection was brief, lasting just a fraction of a second, but it validated Einstein's prediction and launched a new era in astronomy. What happens during a gravitational wave event? When two massive objects like black holes or neutron stars spiral toward each other, they send out waves of energy in the form of gravitational waves. These waves grow stronger as the objects get closer, and when they finally merge, an enormous burst of gravitational energy is released. These waves carry unique information. The mass, spin, and details of the merger are all encoded in their signature. Because gravitational waves are not affected by gas, dust, or electromagnetic interference like light is, they offer unobstructed insight into phenomena that would otherwise be hidden. Why gravitational waves matter? The significance of gravitational waves lies in what they reveal. Traditional telescopes rely on detecting light, which can be absorbed or distorted. Gravitational waves, on the other hand, pass through everything, giving scientists a clear, direct look into events that would otherwise remain hidden, such as the birth of black holes or the interiors of neutron stars. Since that first detection, LIGO, alongside its European counterpart, Virgo, has observed several more gravitational wave events, including neutron star mergers. These observations have vastly expanded our knowledge of the universe and opened a completely new way of studying it. The challenges of detection. Detecting gravitational waves is a technological marvel. The signals are incredibly faint, and Earth-based instruments must overcome interference from things as subtle as traffic, minor seismic activity, and even air molecules. Instruments like LIGO are designed to register shifts smaller than a proton, requiring extreme isolation and noise reduction techniques. A new era of astronomy. The discovery of gravitational waves has ushered in a revolutionary era of gravitational wave astronomy. Each detection peels back another layer of mystery from the universe, giving us insight into its most dramatic events and helping refine our understanding of space, time, and gravity. It's a profound reminder that the universe is not static. It ripples, warps, and evolves. Gravitational waves are not just scientific curiosities. They are the echoes of cosmic history, revealing truths that light alone could never show. Their discovery stands as a monumental achievement in science, driven by human curiosity and the relentless quest to understand the universe in its deepest form. The observer effect is one of the most intriguing and puzzling ideas in quantum physics, sparking both fascination and confusion. At its core, it suggests that merely observing something can alter its behavior. At first, this may sound unbelievable. How could simply looking at something change it? But the answer lies in the deeply counterintuitive nature of quantum mechanics, where observation isn't passive. It plays an active role in shaping the system being observed. To grasp this, think of a common example: measuring the temperature of coffee with a thermometer. In this case, the thermometer simply records the temperature without significantly affecting it. This aligns with our everyday assumption that measurements only provide information without altering what's being measured. But in the quantum world, things are different. Measuring a quantum system can profoundly disturb it. This leads us to superposition, a foundational principle in quantum mechanics. Unlike classical particles, quantum particles don't exist in one specific state. Instead, they exist in a superposition, a combination of all possible states simultaneously. For example, an electron in an atom doesn't orbit in a fixed path. Instead, it exists in a cloud of probabilities, potentially occupying many positions, energies, and spins at once. Only when we measure a particular property does this cloud collapse into a single, definite state. This is the essence of the observer effect. Observation doesn't just reveal reality, it creates it. A famous demonstration of this is the double-slit experiment. When electrons are fired at a barrier with two slits and no measurement is made, they behave like waves, creating an interference pattern as though each electron passes through both slits simultaneously. But when a detector is placed to observe which slit each electron passes through, the interference pattern disappears. The electrons now behave like individual particles. Simply observing the path changes the outcome. This strange behavior raises deep philosophical questions. If observing something changes it, then what is reality? Some scientists and philosophers propose that reality doesn't solidify into a definite form until it is observed, that the universe exists as a set of probabilities until a measurement is made. Niels Bohr, a pioneer of quantum mechanics, famously said, "Everything we call real is made of things that cannot be regarded as real." He was highlighting how quantum particles defy classical definitions of reality. While we assume everyday objects have fixed properties, like a red apple or a four-legged chair, at the quantum level, these properties don't become real until they are observed. Physicist John Archibald Wheeler expanded on this with the idea of the participatory universe, suggesting that observers are not separate from reality, but help bring it into existence through observation. This doesn't mean the universe disappears when no one is watching, but it does imply that observation may influence the properties of what exists. Some even suggest that consciousness plays a vital role in shaping reality, though this remains controversial. Many physicists, however, offer a more grounded explanation. They argue that the observer effect isn't about consciousness, but about the interaction between measuring devices and quantum systems. For instance, in the double-slit experiment, it's the physical interaction between the electron and the measuring device, not human awareness, that alters the outcome. Regardless of interpretation, the observer effect has real-world applications. In quantum computing, systems exploit superposition and entanglement to perform powerful calculations. However, to read the results, the system must be measured, which collapses the superposition into a definite state. Managing this collapse is one of the key challenges in quantum computing. Quantum cryptography also uses the observer effect to ensure security. Any attempt to intercept a quantum communication changes the quantum state, alerting the sender and receiver. Here, the observer effect becomes a strength, offering levels of security that classical encryption can't match. Ultimately, the observer effect reveals something profound about our universe. The boundary between observer and observed is not clear-cut. At the quantum level, reality itself is shaped by the act of observation. This challenges our classical view of a detached, objective universe and forces us to consider a more interconnected and dynamic reality. one where even the act of looking can shift the fabric of existence. General relativity. Imagine standing on an endless, flat landscape with the sun shining above. Everything seems stable and still. Now, imagine placing a massive object, like a boulder, in the middle of this flat terrain. The ground would begin to dip and curve under the boulder's weight. This warping of the surface serves as a metaphor for how massive objects distort the fabric of space and time, what we call space-time, in Albert Einstein's theory of general relativity. A new way of thinking about gravity. Before Einstein, gravity was best understood through Isaac Newton's model, which described it as an invisible force acting at a distance, like the pull that causes an apple to fall to Earth. While this explanation worked well for most everyday situations, it failed under extreme conditions, such as when dealing with massive objects moving at high speeds. Einstein introduced a revolutionary idea. Gravity isn't a force at all, but the result of space-time being curved by mass and energy. In other words, objects like planets and stars bend the very fabric of the universe around them, and other objects follow the curves of this warped fabric, not because they're being pulled, but because they are simply moving along curved paths created by that distortion. Visualizing space-time, the trampoline analogy. Think of space-time as a stretched-out trampoline. If you place a heavy ball, representing a star or planet, in the center, the trampoline will sink, creating a dip. Now roll a smaller ball, say, a planet, across the surface. It spirals inward, not because it's being pulled, but because it's following the curvature created by the heavy object. This is how general relativity reimagines gravity. Light can bend too, gravitational lensing. Einstein predicted that even light follows the curves of space-time. As light passes near a massive object like the sun, it bends. This bending of light, known as gravitational lensing, can make distant stars appear shifted from their actual positions. This effect has been observed many times and strongly supports Einstein's theory. Black holes, extreme curvature of space-time. One of general relativity's most dramatic predictions is the existence of black holes. When a massive star collapses at the end of its life, it can form a point of infinite density known as a singularity. Around this singularity, space-time becomes so warped that nothing, not even light, can escape. The boundary around this region is called the event horizon. In 2019, scientists captured the first image of a black hole at the center of galaxy M87. The photograph revealed a glowing ring around a dark center, the event horizon, just as Einstein had predicted. Time and space are interconnected. General relativity also changes how we think about time. It's not separate from space. It's part of a four-dimensional fabric, space-time. This means that time can stretch or contract depending on how fast you're moving or how strong the gravitational field is around you. For example, time passes more slowly for someone traveling at high speed or near a massive object, a phenomenon called time dilation. This has been verified by comparing atomic clocks on fast-moving aircraft or satellites to those on Earth. Even GPS satellites must account for time dilation caused by both their speed and Earth's gravity. Without Einstein's equations, the system would quickly become inaccurate. Gravitational waves, ripples in spacetime. Einstein's theory also predicted the existence of gravitational waves, ripples in spacetime caused by massive, violent events like black hole collisions. These waves were first detected in 2015, a century after they were proposed. They carry valuable information about cosmic events and offer a new way to observe the universe. Redefining the universe. General relativity fundamentally transformed our understanding of gravity. It showed that gravity isn't a mysterious force acting across space. It's a consequence of space-time geometry. Space and time are not fixed, but fluid and dynamic. They can bend, stretch, twist, and ripple in response to the mass and energy they contain. From black holes and gravitational waves to the expansion of the universe and time dilation, general relativity doesn't just describe how the universe works. It reshapes what we believe the universe actually is. This theory forces us to reconsider the nature of space, time, and reality itself. Fundamental particles, the building blocks of reality. Fundamental particles are the most basic components of everything in the universe, from the tiniest grains of sand to the vastest galaxies. Despite their foundational role, these particles are incredibly elusive and behave in ways that defy our everyday experience. To truly understand them, we must venture into the strange world of quantum mechanics, where classical intuition no longer applies. At its essence, a fundamental particle is the smallest known unit of matter, one that cannot be broken down into anything simpler. For centuries, atoms were believed to be the indivisible building blocks of nature. But as science progressed, we discovered that even atoms are composed of smaller subatomic particles, unlocking a deeper level of reality. This journey began in the 19th century, when John Dalton proposed that all matter is made of atoms. However, early 20th century experiments by J.J. Thomson, Ernest Rutherford, and Niels Bohr revealed that atoms themselves contain a dense nucleus of protons and neutrons, surrounded by electrons in orbit. Advancements in technology, particularly particle accelerators, led to further breakthroughs. It became evident that protons and neutrons were not fundamental. They're made of even smaller entities. This realization gave rise to the Standard Model of particle physics, which identifies the fundamental particles that make up all matter and describes the forces through which they interact. The Standard Model, a framework of matter and forces. The Standard Model categorizes fundamental particles into two main types: fermions, the building blocks of matter; bosons, the force carriers that mediate interactions. Fermions, the particles of matter. Fermions obey the Pauli exclusion principle, meaning no two identical fermions can occupy the same quantum state simultaneously. They include quarks, 6 types: up, down, charm, strange, top, and bottom. Quarks combine in groups, never found alone, to form larger particles like protons and neutrons. Leptons, 6 types, including the electron, muon, tau, and their corresponding neutrinos. Electrons are stable and play a crucial role in chemical reactions, while neutrinos are extremely light and interact so weakly that trillions pass through your body each second without any effect. Quarks and gluons. Quarks are bound together by the strong nuclear force, mediated by particles called gluons. Gluons carry a property known as color charge, which governs how quarks interact. This is conceptually similar to electric charge, but operates under different rules. Leptons and forces. Leptons, unlike quarks, do not feel the strong force. Instead, they interact via the electromagnetic force, e.g., electrons; the weak nuclear force, e.g., neutrinos; bosons, the force carriers. Bosons are the particles that mediate the 4 fundamental forces of nature. Photon carries the electromagnetic force. W and Z bosons mediate the weak nuclear force. Gluon, responsible for the strong nuclear force. Graviton, hypothetical, theorized to mediate gravity. In 2012, scientists at CERN confirmed the discovery of the Higgs boson, a particle linked to the Higgs field, which gives other particles their mass. The stronger a particle's interaction with this field, the greater its mass. This discovery was a landmark achievement, confirming a critical piece of the Standard Model. The incomplete picture beyond the Standard Model. While the Standard Model is incredibly successful, it isn't complete. It cannot explain gravity, which is described separately by Einstein's general relativity; dark matter and dark energy, which together make up most of the universe's mass energy, but remain invisible and mysterious; the seemingly arbitrary masses of particles, which the model doesn't predict. Searching for new physics. Physicists continue to explore theories that extend beyond the Standard Model. Among the most promising are string theory, proposes that particles are not point-like, but tiny vibrating strings. Different vibrations correspond to different particles, and the theory could unify all forces, including gravity, into a single framework. Neutrino research. Neutrinos have tiny masses and rarely interact, making them hard to study, but full of potential to reveal new physics. Dark matter. Though invisible, dark matter exerts gravitational effects on galaxies. A leading hypothesis suggests it's made of undiscovered particles like WIMPs, weakly interacting massive particles. Detecting them would revolutionize our understanding of the cosmos. The big questions. As we delve deeper into the nature of fundamental particles, we're forced to rethink what we know about space, time, and reality. Each new discovery raises profound questions. Are there undiscovered particles or forces? Is there a deeper structure beyond known quantum fields? Can gravity be unified with the other forces? The pursuit of these answers is one of the most ambitious and exciting quests in science. Conclusion: the study of fundamental particles is not just about identifying the smallest pieces of matter. It's about uncovering the structure of the universe itself. By understanding these tiny constituents and their interactions, we gain insight into the origin, evolution, and fate of the cosmos. With each experiment and theory, we edge closer to unraveling the deepest mysteries of existence, those that lie hidden within the very building blocks of reality. Quantum field theory. Imagine standing in the middle of a vast, empty field. Though it appears still and silent, in the quantum world, this emptiness is teeming with activity. This is not an ordinary field, but a quantum field, the foundation of quantum field theory, QFT, one of the most powerful frameworks in modern physics. At first glance, it's hard to believe that empty space is full of energy. But in QFT, even a vacuum is a dynamic arena where particles constantly emerge and vanish in fleeting bursts of activity. Unlike our everyday notion of particles as tiny, solid objects, like marbles, QFT reveals that particles are actually ripples or excitations in invisible fields that stretch across the entire universe. Particles as field ripples. Think of the surface of a pond. Drop a stone, and waves ripple outward. Similarly, particles like electrons are waves or disturbances traveling through their respective quantum fields. The field remains present everywhere, and what we observe as a particle is simply a localized excitation of that field. Each type of particle corresponds to its own field. Electrons, electron field. Photons, electromagnetic field. Quarks, gluons, neutrinos, etc., their own respective fields. These fields fill all of space, and particles arise wherever the fields are disturbed in specific ways. The particles we observe are not separate from the fields. They are the fields. How forces work in QFT. In classical physics, forces like gravity and electromagnetism are treated as separate phenomena. But in QFT, forces are seen as the exchange of virtual particles, temporary, unobservable particles that exist just long enough to mediate interactions. For example, when two electrons repel each other, it's because they're exchanging virtual photons, tiny messengers of the electromagnetic field. These interactions happen continuously, even if we can't see them directly. Virtual particles and vacuum fluctuations. Even in what we think of as empty space, quantum fields are never still. They fluctuate constantly, giving rise to virtual particles that pop in and out of existence. These particles are allowed to exist briefly due to the Heisenberg uncertainty principle, which permits short-lived violations of energy conservation as long as they're quickly resolved. This is why even a perfect vacuum isn't truly empty. It's full of restless energy. This leads to effects like vacuum polarization, where particle-antiparticle pairs appear briefly. Casimir effect, an attractive force between metal plates in a vacuum caused by quantum field fluctuations. Unifying forces in nature. QFT doesn't just describe known particles. It also accounts for the fundamental forces of nature. Electromagnetic force, mediated by photons. Strong nuclear force, mediated by gluons. Weak nuclear force, mediated by W and Z bosons. Gravity, theoretically believed to be mediated by gravitons, though not yet part of QFT. Together, these form the Standard Model, a QFT-based theory that describes all known particles and their interactions, except gravity. The discovery of the Higgs boson in 2012 was a major milestone, confirming that particles gain mass via interactions with the Higgs field, merging quantum mechanics and relativity. One of QFT's greatest achievements is how it combines quantum mechanics, which governs particles, and special relativity, which governs high-speed motion. In QFT, fields behave in a way that's consistent with both theories, allowing accurate predictions even at near-light speeds. This synthesis gives QFT its immense predictive power. It's the reason why particle accelerators like CERN's Large Hadron Collider can discover new particles and validate theories. Open questions and the future. Despite its success, QFT is not yet complete. The biggest challenge is incorporating gravity into the quantum framework. While QFT unifies 3 of the 4 fundamental forces, gravity remains outside its grasp. Theories like string theory and loop quantum gravity are ongoing efforts to bridge this gap. QFT also raises profound questions. What is space if it's filled with invisible quantum fields? Is empty space ever truly empty? Could understanding these fields unlock deeper truths about the universe? Conclusion: quantum field theory has reshaped our understanding of matter, energy, and the very fabric of reality. By showing that particles are not standalone objects, but vibrations of underlying fields, QFT offers a unified picture of how the universe works at the most fundamental level. From guiding technological advancements to expanding the frontiers of theoretical physics, QFT stands as one of the most profound achievements in science. Yet much remains to be discovered. The quantum fields that weave through space may hold the key to mysteries we've only begun to explore.